functions. Okay, refer to them as functions of, okay, function of several variables. It's going to be mostly 2 or 3, but whatever we do, we can do it with n variables. If you are going to be a math major in future, you have a beautiful course. We call it mathematical analysis of the function of several variables, which is going to be a challenging course when you do everything we do in 2-dimensional in the n-dimensional one, okay? So there you are. So let's remind ourselves to see what we want to do again. So calculus 1, x is a real variable. Because the notion of the function is going to be the same, and we have to remind ourselves, okay, so this is going to be the case. X is a real variable. So drop it. We drop it as an input into a function, which is going to be a mathematical function. This function can do addition, subtraction, multiplication, etc. for us. Okay, so the result is going to be y equal to the f of x. Okay, as usual, this is also a real number. Okay, a real number. So y equal to the f of x, we usually refer to it as a real function. Okay, is going to be a real valued function. Okay, real valued function of or in of one variable. Okay, one variable, that variable is x. Okay, so this is whatever we did. Okay, this is whatever we did in calculus, okay, in calculus 1. And we know everything about this function. So what we're going to do, we are going to extend it. The extension is going to be, instead of x to be a real variable, we are going to go to the 2-dimensional. So when you are in 2-dimensional, you are going to have points or order pairs. So the order pair is going to be x and y. So we pick this one in, for example, R2. We are going to be in R2 or in R3 at most. Then we are going to drop this one into a machine. That machine is going to be, again, how you define it, is going to be machine F. Okay, it can be a formula, it can be a chart, equation, etc. That machine would operate on that order pair. The result would be f of x comma y. But this is also a number. Okay, so this is again a real number. This real number usually we denoted by z. So we are going to have z equal to the f of x and the y. And this is going to be called a function, is a real valued function of 2 variables, x and the y. Okay, so z equal to the f of x comma y is going to be a real valued. Okay, it's going to be real valued function. Okay, a real valued function of 2 variables. Okay, of 2 variables. And the variables are going to be x and y. Okay, so we change it into a function of 2 variables. So if you get a triple here, your triple will be x, y, z in R3, and the result is going to be the same. Okay, so there you are. This is going to be our, we are going to stop here. The other case is going to be, you get these 2 in R2, then you pick this one to be, again, either in R2 or in R3. So that would be the thing that we're going to do in chapter 15 when we get to the end of the course. But we stay here. So this is going to be a function, you see, is a real valued function of 2 variables. And the condition of the function is as usual, as you had it before. Okay, so officially, this is going to be our function, and this is going to be official definition. I just want to motivate it to see it's the same thing. So officially, if D is going to be define everything in R2 and R3, so D must be a subset. If D is a subset, D would be our domain. if T is a subset of points this time, okay, of points in R2 in two-dimensional space, okay, then we have a function. This function f is defined from D into the real numbers, okay, this function, and it's going to be denoted by z equal to the f of x, y, okay, and what is this? This is going to be, as usual, is going to be a formula, okay, so is a function, okay, is going to be a function of two variables, a function of two variables, x and y, if, okay, I'm sorry, just the same definition for the function. So what is the condition? The condition is you are going to have for each x and the y, you get only one z that satisfies this condition. The same thing, so if f relates, as we did it with the function of one variable, relates each point, relate each point x comma y in the domain D to exactly one, okay, exactly a number, exactly a number in R such that, that's official definition of a function, okay, is such that, so exactly a number, let's say a number z, a number z in R such that we have z equal to the f of x comma y. Okay, this is official definition of a function, and it's going to be always the same. You can, you know that you can even define this function for the vector spaces. Okay, any question? So D is a subset of R2. So you are in the domain, you are going to have ordered pairs. You drop it into the machine. Machine is depends. Okay, this the machine can be addition, subtraction, multiplication, etc. Okay, so in that case, now similarly we can extend it. Okay, similarly in general. Similarly, if x1, x2, that's the next step, x3 up to the xn are going to be numbers, okay, are again real numbers, okay, real numbers, then we can define, okay, then your function would be f of x1, x2, x3, up to the xn. We go only with the three variables in this course, of course. Okay, this can be defined. Okay, this can be defined as a function, of n variables. Okay, function of n variables. N variables, x1, x2, up to the xn. Okay, so easily we can introduce our function and the notation that we are going to use. Any question? So make sure you understand where are you, where is your domain. Okay, your domain is coming from the R2, R3, or Rn, but your range, okay, the result is a number. So it's going to be a number, and most of the things in calculus 1 or the function of one variables can be easily generalized. Okay, so this is our new objects. These are going to be the objects in this chapter 13. So let's try to see what you can do with this function. Any question? First, let's work with this function. Okay, the way we are going to work with. Okay, just keep it so you can write it down. So mainly we go with the X, Y, Z here, and we, whatever we do at the end of each group of examples or theorems, we give one example with the 3 variables. They are going to be the same, but we need them. We go to the 2-dimensional and the 3-dimensional in future. Okay, are you done? So we're going to the first thing, let's work with this function. So your first job is evaluation. You have some problems in your assignment. You better do one of them. You see this the way you pick your problems. Make sure you pick the one that corresponds to my examples. So that would be helpful for you. So this is the first one. The first group of your assignment, just evaluation. A function will be given, they ask you to evaluate. I just want to show you that you'll be fine to do it. This is it. For example, I pick this function. So you give you a group of them, it's given to you. Suppose your function is f of x, comma, y, which is equal to the 3x squared radical y. You say this is a function of 2 variables. The result is a number. Then, for example, they ask you to find the following. So don't be surprised. They ask you to find what is f of 1 and 4. Okay, what is f of t squared and t? Okay, and they ask for what is f of AB and the BA. Okay, these type of ideas. You know that the function is a machine, so you drop these numbers, you plug in, and you get the result. Okay, so the solution is going to be, so the first one, f of 1 and 4. So you go to the function and you replace the x by 1 and the y by 4. Carefully subset, it's going to be 3 times the 1 is squared and the square root of 4. So square root of 4 would be 2. So that gives you 3 times 2, 3 times 2, which is equal to the 6. So we say that the value of the function at 1 and 4 is simply equal to the 6, and we're done. So you connect the point 1, 4 to a number 6. Any question? So not big deal, but we have to get used to it because this is our work, our job. The first one is this one. So we'd like to get what is f of t squared and t. You go to the function and you replace the x by t squared and the y by t. Okay, so that's going to be 3 t squared squared. Okay, the radical t. So t squared squared would be t to the 4th. So that gives it 3 to the 4th radical t. And then you done. Okay, you simplify the number part. And the last one, you want to find f of AB, BA. So again, you go to your function and you replace it by the corresponding numbers, values. AB is x, BA is y, and this is our function. So it's going to be 3 times x squared, which is going to be AB squared, and the radical, okay, y, which is the BA. The only thing we can do is just square this one. That gives it 3a squared, b squared, radical BA. And that would be the final answer. Okay, so that's going to be evaluation of the function. Okay, to get to know it, this is the say we are going to operate is like a new calculator. Any question? So that's evaluation of the function. Now your next main job, or officially your first job, is how we're going to find the domain of these functions. Okay, so again, pick a couple of them in your case, your sets of assignments. We would like to find the domain of each function. So find the domain of this function. The domain of each function. You know, the domain in this case is going to be the points that can pass through this machine. So the restriction that you have, because the result is a number. So there are some restriction for the numbers. So say no restriction for adding, subtracting, multiplying. If you divide, the restriction is you cannot divide by 0. If you take the roots, if you take the even roots, the restriction is the number must be positive. Okay, so the same thing that we did before. So the first group are, of course, this is it, the famous one, f of x comma y, and it's x squared, okay, minus 5x times y plus y cubed. Again, as a function of one variable, you look at these operations. Operations are going to be addition, subtraction, and multiplication. And x and the y are numbers. So we know that there is no restriction for adding, subtracting, and multiplying. So this function is defined everywhere. It's a polynomial function in two variables. You see x and the y. So it's like the one that you have in a function of one variable. So the solution is going to be this, the way you are going to describe it for us. So I just explained that f is a polynomial function. Is a polynomial. Okay, it's going to be a polynomial function, but in two variables, just for your information, in two variables. Two variables, and of course it's defined two variables, x and y. Okay, so it's a polynomial, it's defined everywhere. So it is defined. Okay, it's going to be defined everywhere, but be careful. Everywhere there, domain are coming, you see two variable domains coming from R2. So we say that it's defined everywhere in R2. Store information, but basically the domain is all points in R2. Some people, they made a mistake. They say it's defined everywhere on R. Remember, the domain is subset of R2 when using two variables. So you have to say that it's defined everywhere in R2. Any question? So get to know them. Polynomials in this case is a polynomial of two variables. So that's the first case. The way they put the restriction for you, they usually give you something like the ln function or the radical function. So this is the next case, f of x comma y is going to be ln of x squared minus y. It's a ln function, but it's a ln of two variables. Then you know the restriction for the natural log. The restriction for the natural log is, you know, that you cannot find the ln of a negative number. So you have to impose this restriction, okay, to get the domain. So your solution is going to be, remind yourself that f is defined. Of course, it's defined with one condition, when this x squared minus y is greater than 0th degree. Okay, we usually move the y to the other side. So it would be y less than x squared. You have to describe this one. Okay, this is the way we do it. You are not going to leave it as is. You are not done. You have to give us a domain as a set, as a subset of R2, as a collection of points. Otherwise, you are not going to get the, otherwise you haven't described it nicely. So domain, this is the way you write it down. Domain is a collection of points, x comma y, collection of points in R2 with one condition. The condition is y is less than x squared. So this is the way you're going to give us a domain. Okay, be precise. Some people, they say domain y less than x squared. Doesn't make sense. It must be a subset of R2, so nicely describe it. A collection of points that satisfy this condition. Any question? There is another way to describe the domain using geometry, but we like the abstract form, but the geometric form is interesting. Okay, so it's not bad to look at it. So y equal to the x squared is going to be a parabola. You don't have the equality sign, so we're going to write it as a dot curve. You see, this is going to be this dot would be y equal to the x squared. And the points you are going to be interested in is the one that satisfy y less than x squared. You know that y less than x squared would be all the points below the graph, if you like. So these are going to be, okay, so this is going to be the domain of the function, if you like, if you like geometry to get it. But we need this one on the test, remember. If you describe it nice, but we need abstract form because the domain is a subset of R2 officially. Any question? So be aware of the natural log. It doesn't matter, natural log is natural log always. So we don't use any complex numbers, anything. So the domain is where the input is positive, strictly, and that's how you describe it. This is one group. And the other groups are going to be more popular in this course as we go on. Are you done? So what's going to be the next group? This is a very popular case. Okay, and this is number 3. The restriction that can impose are going to be this one, f of x, comma, y. It's kind of a rational function, but on the top we have something like x squared plus y squared minus 9, everything inside the radical, divided by x. Okay, that's 1. It's a rational function to start with. Restriction on the rational number is the denominator cannot be 0. You know that these part are all numbers. So one restriction that we have to impose is that the x is not 0. But on the top, we have a square root function. Restriction for the square root function is the inside cannot be negative. So you have 2 conditions to satisfy to get your domain. So this is how we're going to describe it. Or check it for yourself. You say, oh, okay, f is defined. F is going to be defined when these 2 conditions are satisfied. It's defined when one condition is that the x cannot be equal to the 0. And the other condition is the top. You have to make sure that the x squared plus y squared plus 9 minus 9 is never negative. So this must be greater than or equal to the 0. Okay, so write it down in a set form. So in a set form, your domain is going to be a collection of points in R2. It's going to be x, comma, y with the condition. So the condition that you need are going to be, you can move the 9 to the other side. So this is going to be x squared plus y squared, strictly bigger than 9. Okay, and of course, the condition that x cannot be equal to the 0. Okay, so it's kind of the point outside a circle. So we get I think that's going to be the case if you want to describe it. If you want to describe it, is going to be you have outside a circle with the radius 3. So going to be 1, 2, 3, and that's a 1, 2, 3. Just for your information, 1, 2, 3, and the 1, 2, 3. Okay, so we have this circle, and there is no equality sign here. So I got the, okay, I got this circle. The points must be outside of the circle. Okay, so the outside of the circle are going to be here. Okay, and the x cannot be 0. So you have to take out, I think, this part out. So you have to take this point. So I just take this to be a dot because x squared plus y squared must be. Okay, so these points are going to be out, if you like. I think that would be the case. So, and we put those. Oh, yes, you are right. It's greater than equal to, so I have to solid this. Okay, it can be the points on the circle. Okay, the point on the circle. And you have to take these two out because this is where you give you x equal to the 0 and x cannot be equal to the 0. Okay, so, you just describe it as a collection of points and we accept it. Okay, we need the abstract form, not not the geometrical form. Any question? So get used to this type. This term is going to be repeated for the continuity. So we should give you one with the 3 variables. That would be usually is this case for the test. Any concept, we talk about it in this chapter, or just, we just give you one of those 3 variables too. So the 3 variables case are going to be this one, f of g of x, y, z. So now your domain must be a subset of R3. So this is the function. Again, the popular formats are these, and you have again some in your book that you can pick to practice. And you have the 9 minus x squared minus y squared minus z squared. Okay, so that would be your function. Again, it's a rational function. You have to focus on the denominator. But the denominator happens to be the square root function. So we have to focus on the fact that the inside cannot be negative. Okay, so the inside must be positive and inside cannot be 0. So you don't have the equality sign because the denominator would be 0. So it's easy to describe it, to say that G is going to be defined. Okay, G is defined. It's going to be defined when this denominator 9 minus x squared minus y squared minus z squared is going to be a strictly greater than 0. The radical by itself can be greater than equal to the 0, but since it's done the denominator, so you exclude the 0 as well. Okay, and we usually move the 9 to the other side, so we get x squared plus y squared plus z squared less than 9. So it's going to be popular domain. You know that x squared plus y squared plus z squared equal to the 9 is going to be a sphere. Okay, it's going to be a sphere, but it's less than 9, so the points are going to be inside of the sphere. Okay, so it's a very popular domain for future as a collection of points. Your domain, your points are in 3-dimensional R3, so you have to give us a collection of points like x, y, z, such that x squared plus y squared plus z squared is going to be less than 9. It's a popular domain for integration at the end. Okay, so just make a note for yourself that this is the point inside the sphere. Okay, so this is going to be the set. Okay, it's not bad to make a note. The set of points. Okay, the set of points inside the sphere. Okay, a sphere with the radius 3. With the radius 3. Okay, so that's the best domain that you can have for the function of the 3 variables. Okay, any question? So these are just get to know the function that you're going to work with for the domain. The other thing that we do is, so you have the domain, so how about the range and the graph of the function? Okay. So let's say I'm going to describe the graph of these functions. Remember, the graph is a collection of points. So if you have a function of one variable, y equal to the f of x, your graph is going to be the collection of points in two-dimensional that satisfy y equal to the f of x. So it's going to be the same for the function of several variables. Okay, so let's describe the graph because we need it, the graph of these functions or the description of the graph. And the question that would be given to you, you are going to be asked to find the domain, the range, and the graph of the function. This is going to be one of those 6 questions that you're going to see in quiz number 2 at the end of the week. Okay, so let's remind you what's the graph of the function. Remark. Okay, a graph of the function, graph of a function. Graph is always a collection of points. It doesn't matter which function you're going to have. So let's recall from calculus 1. Okay, we recall that if a function is given to you by this equation, if y equal to the f of x is going to be, okay, is a function, is a given function. Given function, then the graph is going to be a collection of points. Then its graph is going to be a collection of points, is the collection of points, satisfying this condition, if you like. Okay, so the graph of the function is going to be simply a collection of points x and y such that y is equal to the f of x. Okay, which is the same as the collection of points of x and f of x when x is in R. So you describe the graph of the function of one variable. Okay, so your function is a function of a variable. Your graph, of course, is going to be two-dimensional. It's going to be, on the plane. Okay, so if you have a function of two variables, okay, so similarly, if you like, if z equal to, okay, so if z equal to the f of x comma y is a given function, then the collection of points okay, then you are going to have what? So the graph of the function is going to be a collection of points that satisfy this condition. So you are going to be in three-dimensional. Okay, x comma y comma z such that z equal to the f of x comma y. Okay, this time it's going to be the same as x comma y. Okay, and comma your function, which is going to be f of instead of z. Okay, and this is going to be true when x and y are numbers. X and y are again numbers in R2. Is going to be the graph, okay, graph of the function of z equal to the f of xy. So basically it's a collection of points that satisfy the given equation. But you got to be careful, okay, to make sure that, okay, where you are, okay, to get these functions. Okay, so, and this is it. So we give one example. I'm going to describe it. Any question? So get to know it. Just set the notation. The things are going to be different. Okay, and then you just want to make sure that you are able to do it. Okay, are you ready? That's it. Describe. Okay, describe the graph. Graph of each function. Number one, f of xy is equal to 1 minus x minus 1/2 of y. Just give you a couple of minutes to think about it. I have something to check here. Is going to be the case. Okay, sorry, I got the message from the APC regarding one of those questions. I have to answer them right away. Okay, there you are, the function. What's the domain of this function? Any suggestion? Just look at the function, look at the formula that we have. 1 minus x minus 1/2 of y. Just check to see if there is any restriction on this one. Okay, all what? Danny, you have to describe it. What do you mean by all? Do you mean all points, numbers? Okay. No. No, the domain. Real numbers in R2, no, doesn't make sense. When you are in R2, you don't have numbers, remember? When you are in R2, you have points. So points in R2. Whatever you do for the function of one variable, you say all real numbers. Yes, because you are in a real number set case. But your domain, you see when you say x and the y, your domain are going to be points in R2. It's a kind of a polynomial, no restriction, so the domain is going to be all points in R2. So the domain is R2. Okay, just to make sure the way you describe it, you use it, the correct term. And so it's defined everywhere, but everywhere on R2 because of this. Okay, so this is it. So note that the domain is R2. Yes, x and the y can be any real numbers, but you are in two-dimensional. Okay, the domain is two-dimensional. So describe it, yes, all points, that's correct. Okay, that's it. Now what's going on to the graph? The graph is going to be in R3. And the graph of f, okay, the graph of f is what? Is, you see, a collection of points x, y, z that satisfy this condition. Z equal to the 1 minus x minus 1/2 of y. You see, this is your graph. Now you have to give us a description of this equation. So let's see if you know this equation in R3. Note that I simplified a little bit for you to help you. Z equal to the 1 minus x minus 1/2 of y is the same as what? Z plus x minus 1/2 of y equal to the 1. In R3, can you tell us what is this one? In R3, what this would describe for us? Points, a plane. Yes, you are right. And it does, that's it. Yes, you see this is the equation of the plane. Remember, ax plus by plus cc plus d equal to 0. So in R3, this is is going to be a plane. Okay, a plane in R3. Since they ask you to describe it, so you have to tell us what it is. Mathematically, this is correct. You say that's it, yes. This is going to be the graph of your function, because the graph is a collection of points. But it's for you to get to use it. You know, it's a new things. It takes a little bit of time, but we'll be fine. So from now on, we have to change our habit from the real numbers to the R2, R3. Okay, so we get the description of this equation in terms of the Z. This one, these are the one that's popular. We're going to use it. So I want to know it. Any question? So this is how we describe the domain or the graph of this function. Ready for the next one? So I give you another very popular one, just to get to know these new terms, objects that we have. So what is going to be this one? This is also interesting. Use it quite a lot. So how about this function? F of x, comma y equal to the square root of 1 minus x squared minus y squared. You want to know what's going to be the graph of this function? Of course, you have to get the domain first. You see, to see where you are in the domain, then you get the description of the range. Okay, so to get the domain again, you have points in R2. Is there any restriction for your points? Yes. We have the square root function, so the restriction is going to be, you have to guarantee that you are not going to get a negative number here. So this is how we're going to define it. Solution. Okay, so there you are. F is defined. F is going to be defined. Okay, if 1 minus x squared minus y squared is greater than or equal to 0. And you know this, so this means you are going to have the x squared plus y squared less than or equal to 1. So your domain is going to be a collection of points in R2. So the domain is a collection of points x, comma y that satisfy this condition, x squared plus y squared less than or equal to 1. And you know what it is, this one. Okay, any suggestion? What shape of this domain in R2? In R2, it's going to be a circle. It's a point in a circle in 2-dimensional. Okay, a domain is in 2-dimensional, x and the y. Since you are in dimensional, so it's going to be the point inside the circle. Okay, point inside the circle. Yes, inside and on the circle, if you like. These are going to be your domain of integrations in future. Okay, but we are interested in the, okay, we have to describe the graph. So your graph is going to be in 3-dimensional, so describe it first. So what is going to be the graph? Note that. again, you get your graph. So note that the graph of the function, the graph of the function. So your graph is going to be in three-dimensional. So is going to be is the collection of points x, comma y, comma z, such that z would be equal to what? Z equal to the f of xy, which is going to be z equal to the 1 minus x squared minus y squared. Okay, so this is going to be the graph of your function. Okay, you write it down to get the z. Now you are going to be in three-dimensional. So work on this one to see what is this. Is z equal to the, okay, let's check this one. So the checking is going to be, again, we note that if we can give you a description of this equation, so z equal to the 1 minus x squared minus y squared. Okay, you better square it. Z squared equal to the 1 minus x squared minus y squared. So that gives you x squared plus y squared plus z squared, which is equal to 1. And you know this one. Okay, what is this one? Geometry. This is going to be the sphere. Yeah, it's a unit sphere. Unit sphere. But what is the graph of your function? This is where you got to be careful. You see, so go back and put it here. And note that, you see, your net is note that again, your z is greater than or equal to the 0 because you take the square root. It's going to be equal to the 0, so you are not going to have all the points. Okay, so this is going to be the case. You see, so the graph is going to be the graph of the function, okay, of f is going to be the collection of points x, y, z that satisfy this condition. X squared plus y squared plus z squared equal to the 1, with the condition that the z must be greater than or equal to the 0. Z must be greater than or equal to the 0. Any question? Can you describe this one for us? Describe it from any suggestion? X squared plus y squared equal to 1 with the condition that z greater than or equal to the 0. All points inside the sphere, all points inside the sphere. No. Better description. Anything else? Z positive. Not inside in this case. We have a special name for this. When we go with the sphere, you see it's like a circle. When you have a circle, you see x squared plus y squared to the 1. If you solve for x or y, if you want to take the square root, you see, if you want to solve this one for z, you get z squared with the 1 minus x squared minus y squared. If you take the square root, there are going to be positive negatives. So when we get a positive, in the case of the circle, is going to be upper semicircle. When it's going to be negative, it's going to be lower semicircle in the case of the circle. If you are in three-dimensional, okay, semicircle would be changed into what? Into the hemisphere. So it's going to be upper hemisphere and the lower hemisphere. So in this case, it's going to be upper hemisphere. Okay, it would be used quite a lot in this course, in this domain and the graph. So pay attention to it. So we say that it's like a circle. And when we get a positive in the case of the circle is upper, okay, upper semicircle and the low. You see, when you get the circle, you see if there's going to be a circle. So it's going to be the upper part and the lower part. Remember, for the equation of a circle, for example, this would be y equal to the 1 minus x squared, and this is going to be y equal to the negative 1 minus x squared. So it's the same for the sphere. So when you take the square root here, you have only this one, so it's the upper hemisphere. So it is the upper hemisphere. Upper hemisphere with the radius, radius 1. It's a very popular domain, again, for integration at the end of the course. We have something, we call it spherical coordinates, those great theorems in chapter 15, and this is very popular domain over there. So that's why I want to just get used to them. It's just right at the beginning, we are going to make different excuses to introduce this. Why is not z squared greater than equal to z squared greater than equal to the 0? Not z squared, just z. This one? You see, because in your restriction, z is the square root. So you get a, you know that the square root is always positive. So z is greater than equal to 0. We have nothing to worry about the z squared, because z squared is always greater than equal to the 0. Okay, so the function, look at the function that we have. You see, your function is the square root function. Since the square root function, your z, you see, this is it, your z is greater than equal to the 0. So when you take the square root, you just take the square root of a positive part. So that's why when we get the positive part, you are going to be on the upper hemisphere. You see, that's going to be upper hemisphere, and this is the type that you have for the sphere. So the upper and the lower is going to be the case. Okay, in future we are going to change it to the, we use the trigonometric equation to change it to the cylindrical, spherical. So it would be lots of story about it. So it's very popular one. There is 1 minus, you get 4 minus, 9 minus, 3 minus. So make a note of this very popular one. Okay, and so this is going to be the case. Any question? Very popular case to remember. Now there is another one, very similar, but it's going to be different. Again, we need to know this before be able to get to the other parts. Let's see what's special about this one. It would be quite interesting. Let's look at this. F of x comma y is equal to what? Is a negative square x squared plus y squared. Look at this. That would be interesting to get this one. So start with the domain. What's the domain of this function? Any suggestion? You have x and the y. Okay, your result is a radical function. Of course, there is a restriction or the radical function, but your radical is a square root. So the restriction for the square root is what? Is that the x squared plus y squared cannot be negative. We know it. X squared plus y squared is always positive. So we have no restriction. So the domain would be, we can use all the points. Okay, so the solution is going to be, and we note that whatever we do, x squared plus y squared is always greater than or equal to 0. Okay, so we have no restriction. This is true for all x and y. So the domain, again, the domain is in 2-dimensional, is R2. It's true for all x and the y, but your domain, you have to describe your domain in 2-dimensional, which is R2. Any question? Range. Let's say I'm going to describe the range. For the range of the function, I give another method. You say just go introduce this one like a C. So also get the description. You have a z equal to the negative x squared plus y squared. You want to get the description of this. So as usual, square it. That gives you z squared. Okay. What is this one? If you square it, that gives x squared plus y squared. Okay, that is going to be the case that you're going to have. Okay. So the graph of the function, you see that give you the one as soon as you, but you make a note that your z is less than equal to the 0. You see, because when you take the square root, it's going to be positive, negative. So what's going to be the graph? The graph of your equation is going to be a collection of points, x, y, z, that satisfy this condition, the condition that the z squared is equal to the x squared plus y squared, and z is less than equal to the 0. Can you describe this one? Do you remember? Of those graph that we describe, this is going to be ellipticoid. Is not elliptic. Or is it? No. You can say that elliptic, but the better one is circular coin. You see, because this is x squared plus y squared, you know that if you replace the z by a number, that gives you a circle. So it's a circular coin, okay? So it is a circular coin. It is, you can use your calculator, graph it, you will see it, a circular coin, like an ice cream, with z to be less than equal to the 0. Okay, so these are going to be a kind of functions that we are interested in for future, okay, to get to know them. So it's good for you to know, to get to the feeling of how you are going to operate with these new tools that you have. Okay, so study this carefully to be able to do it. Any question? So I'm going to put them together, give you one example, the kind that you have in your book, or the kind that from this section you are going to see on your next quiz and the test. We give one function and we ask you to describe what is the domain, what is the range, and what is the graph of the function. So if you want to check, you have a couple of them in your book. You better pick one of them and take care of it, okay? So this is the conclusion of this section. Okay, the conclusion of this section is this problem. And this function is very popular. You're going to use quite a lot in future. That's why they give you this one. You want to find the domain and the range. Find the domain. Okay, and find the domain and the range output of this function, like the one that we did. F of x, y is equal to the square root of, it's 16 minus 4x squared minus y squared. Okay, find the domain and the range, and then they ask you to describe the graph of the function, the graph of f. This is typical problem for this section, the conclusion of this introduction one that we have. Okay, are you ready? Start with the domain. What's a restriction? Restriction is what? The function is a square root function. So we have to guarantee that this inside is never negative. So basically, this is how we're going to describe the domain of your function. Solution. So restriction, you focus on the fact that f is defined. F is defined, of course, if or when inside 16 minus 4x squared minus y squared must be greater than or equal to 0. Okay. We can make it better. Let's move this to the other side. If you like, these are optional. So that would give you 4x squared plus y squared less than or equal to the 16. Even you can go on, divide by 16 to get a better description of your domain. 4x squared over 16 plus y squared over 16. And this is going to be less than or equal to 1. So we simplify this one by 4. That gives you x squared over 4 plus y squared over 16, which is going to be less than or equal to 1. Okay, so the description of your domain, the points in R2 that satisfy this condition is going to be x comma y that satisfy the condition that x squared over 4 plus y squared over 16 is less than or equal to 1. This is your domain, the best way to describe it. Any question? Can you describe it in geometry? What is this domain represent? The domain represent, yes, ellipse. Yeah, that's going to represent the points inside. It's going to be the points inside an ellipse. You know that if they are going to be equal to each other, that would be circle. In that case, it's going to be an ellipse. Okay, so it's going to be points inside. So these are going to be points. These are just optional, but it's good to remind yourself, get to know this region for future. So it's going to be points inside. Point inside and an ellipse. So that is domain so far. Any question? Mathematically, you are done. Even if you write this first one, we accept that. And when they ask for the domain, you just give us the fact that it's a collection of points. It's a collection of points that satisfy this inequality. We happy. But it's always nice to show off your knowledge. Okay. The challenging one is going to be the range. Remember, this is a real valued function. The domain is in R2, but the range is a subset of real numbers. So you have to describe it for us. Okay, now let's see how it's going to be the restriction. When you put the numbers in X and the Y, what are we going to get in the result? What type of numbers are going to get? Or that's going to be your range. Okay, so this is how we're going to describe the range. To find the range. Okay, this is it. The output to find the range of F. You see, this is your Z. Your Z is going to be 16 minus x squared minus 4x squared. Okay, 16 minus 4x squared minus y squared. You see, the range is going to be the Z. So you know that this Z is greater than or equal to 0 because it's the square root. So in one side is greater than or equal to 0. On the other side, you see, look at this one. This can be written as 16 minus 4x squared plus y squared. You see, this number inside is always positive. So if you take a positive number out of 16, the result is going to be a smaller. So this is going to be always less than or equal to the radical 16. Okay, because this is 16 minus. And radical 16 would be 4. So your Z is going to be greater than or equal to the 0, and it's going to be less than or equal to 4. So what's going to be the range of the function? You see the range of your function is going to be closed interval of 0 and 4. This is the range. Of course, it's not easy to find most of the time, but they give you something. It's always, they give you something symmetric here that you take it out and then you get the inequality right away. Okay, so the range of the function is going to be just the result. There is a restriction of the result because the square root, so it must be positive. And on the other side is, just a trick that we are going to use in order to get it. Again, it's not easy, but this is what we do. The zero part, this is it, z is a square root. You know that the output of the square root is not a negative number. So it's always greater than or equal to 0. Okay, so your range is, to start with, the range of the function is a subset of positive numbers because of the square root. So that's to start with. Always you have this, but you have to find the other part. Okay. So this is going to be the range. And now description of the graph. Okay. So the graph of f, just describe that z, the graph of f. And so to get the description of the graph is going to be, that it's going to be a collection of points. That is going to be x, y, z that satisfy the condition that we have. Okay, the condition is z equal to the 16 minus 4x squared minus y squared. We already described this one. Okay, this is going to be the fact. So of course, z is greater than or equal to the 0. Again, you can go back and simplify it, get the description. You already got that description. Okay, so for example, in this case, again, you start with the z. You do whatever we did for the first part. To get the description, z squared, you square it, 16 minus 4x squared minus y squared. Again, you move everything to the one side. This is going to be the case, plus z squared equal to the 60. Okay, you know that this is going to be an ellipse. So this is, you can continue to write it down in the ellipse form. If you like, you can divide by, you don't have to. You can divide by 16. So this is going to be 16, and you simplify this part. So we get the fact that the x squared over 4, y squared over 16, and the z squared over 16 is equal to 1. So it's going to be an ellipse. So there you are, x, y, z, such that x squared over 4 plus y squared over 16 plus z squared over 16 equal to the 1. But remember the condition, z greater than or equal to the 0. So this is an ellipse, but since z is positive, upper part of the ellipse, if you want the description, is going to be, so the graph is going to be the points. Okay, the points on the upper part of an ellipse. You see, this is going to be the result that you have. So they are very popular, to work with the, that's why you just, you just work on those quadratic surfaces, because these are the one I told you, going to be the domain of your function. Okay, so that is the first part of the argument of a function of 2 or 3 variables, the domain, the range, the graph, and how we're going to work with it. We give a break, we come back, calculus. So I'm going to find the limit. Okay, limit, continuity. It would be a little bit much more involved. And the limit is the most important part. Just give you a short one today, and then we continue. Okay, any question? So the 12:02:05, so we just come back in 10, 12 minutes, and I give you a little bit description of the limits. It's quite interesting. It's not difficult, but you have to make sure you understand it. But working with this is easy. So see you later. Okay, so we introduced the function of two variables, okay, or three variables. Now we have a special machine, so we are going to operate with this machine. What's going to be the calculus of this type of functions? Okay, so we have to take the limit of a function. Okay, let's say what is your refreshing your memory regarding the limit of a function of the real variable, okay, or the one variable in calculus one, and then then the limit's going to be very much similar, okay, for some parts. So let's review first. What is going to be the limit of the function? Okay, so we review first. Make sure you understand what's going on for the limits. Okay, so what is going to be the limit of a function? What is the limit of a function? Y equal to the f of x. Remember, limit is an estimation. You estimate the value of the function around the given number. So this is just the way you did the definition of the limits. So we recall that we usually write the limit of f of x when x goes to x0 is a number like L. Okay, if and only if when x getting closer and closer to the x0, then this f of x getting closer and closer to the L. So this means if and only if f of x would be approximately L, if you like, f of x would be approximately L whenever, it's very informal, x is approximately x0. Okay, which is equivalent to the fact that the difference, there are numbers, so we can use the absolute value. The difference of f of x minus L goes to 0 whenever, okay, the difference between x minus x0 goes to 0. So that's a very informal way we are going to write the limit of the function. Okay, so what does it mean really? The meaning is this one, that you see the limit, the precision, the limit is going to be estimation. When you estimate, you may lose something or you may gain something. Okay, it's like rounding. When you round it, you may round it up or you may round it down. So when you do the rounding, you say, oh, I'm rounding this one up to the 10th place, up to the 100th place. So the 10th and the 100th place is going to be your tolerance. We call it percentage of error. So basically, this version of the limit, this means I can estimate, I can make f of x as close as you like to the L, or I can estimate the values of f of x, okay, by L, as close as you like. It means you just give us your percentage of error. If you want to do it up to the 10th place, 100th place, etc. How are we going to do it? By forcing the x. By forcing the x to be as close as I like to the x0. You see, that's going to be the notion that we're going to use. So equivalency, again, this means equivalency. I want to change it to the format that you are going to use in this course. There are cases that you have to use the definition to do the job in this course. That's why. So equivalently, this means another version. This means the limit of f of x when x goes to x0 is equal to the L if and only if only if one can, or one can estimate f of x by L, that number, as we like, as one wishes, if you like. Means you give us the percentage of error, we're going to do it for you. How are we going to do it? By selecting, okay, by selecting values of X, selecting values of X that are sufficiently close to, okay, close to X0. That's the abstract version of the limits. So this means you tell me what you want, I do it for you. So I do it for you. You know that there is going to be an X. You move the X first, then you get f of X. So you tell me how we're going to estimate this one for you. Then I'll go and do something to the X that give me the, you know, the similar, the similar one. So this means I can, okay, this means if and only if. When we say one can estimate f of X as you wish, you give me your wish, your percentage of error. So you may say that I would like f of X to be close to the L with the percentage of error of 110, 100. So you should give me that. So we say that if and only if. This is a famous epsilon delta definition of a limits that was given by Agustin Cauchy first and later on by Carl Weierstrass. So this is going to be true if and only if for any given percentage of error, given number, given positive number, we usually refer to that number as epsilon or epsilon. E stands for the error. So that's a percentage of error. So you give me your tolerance, I do it for you. For any given positive epsilon, then I have to force the X. I can find there is, this is percentage of error for X. There is a positive number. There is a second positive number that I'm going to find it. A positive number. Okay, delta, positive, such that if 0 less than absolute value of X minus X0 is going to be less than delta, then f of X minus L is going to be less than epsilon. It's a famous definition, and we don't usually cover this one in full details in calculus 1. So you may have heard about it, but it's going to be useful over here. We have to do it here. Okay. So this means when I say the limit of f of X, X goes to X0 is L, this means I can make it, I can estimate it as you like. You just give me the percentage of error. So that's going to be for any given positive number epsilon. That is the estimate that you would like. I can do the similar estimate for the X. We call it delta. So when I find it, this machine would automatically operate, okay, to get these true. So this is the famous epsilon delta definition. Epsilon delta definition of the limit. Of the limit of a function. Okay, this is very famous, this definition. It was the time that when the limit was discovered, okay, they just used that expression X approaches X0. But there was a time in Europe that the mathematician believes that a group of mathematicians headed by Lagrange, they believe that every definition in mathematics can be expressed in terms of an inequality. And it was Lagrange who just proposed a prize for somebody who can come with the definition of a limits in terms of the inequality. That was Agustin Cauchy who just bring this definition first. Okay, it's the definition of a limit in terms of the inequality. And of course, later on, it was extended by Karl Weierstrass. Let me just give you one example to see how this would operate, because we need it in case you haven't done it in Calculus 1. So we get some idea first, and then we go with, we extend it. The extension would be easy now that I do this formula. Okay, are you ready for one example to see how we operate, proving the limits, if you like? This is the example. We want to this is it. We want to prove really. Suppose you already find this limit. You see the limit of f of 5x plus 1. When x goes to 1, you know that that's a polynomial. It's going to be equal to the 6. We want to prove it by this. So this means I can estimate 5x plus 1 by 6, as you like it. As you like it, you have to tell us what's your like, what's your tolerance. How much are you going to prepare to lose or gain? That would be epsilon. Okay, so suppose I give you that. We wanted to find, okay, find the values. Values of x such that the difference of 5x plus 1 minus 6 to be less than 1 over 100. So this means, you know, when you find those values, you find those estimate for 5x plus 1, you are going to round it up to the 100th place to get the 6. Okay, so this is the meaning, rounding up to the 100th place to get 1 over 100. Okay, so tell us what to do. Remember, you prepare a table to be able to do it. So you just tell us how we're going to prepare that table so that if you pick any number on that table, this estimate would be less than 1 over 100. Okay, everybody understand the question? Any question? So we want to actually do it, not the way, you know, we did it before. Okay, this is the way we're going to do it. We work on this one. You have to connect this one into the x to the 1. So the solution is going to be, so you start with the given one, 5x plus 1 minus 6. You want to find the x here. So this would be 5x plus 1 minus 6. Combine the like terms, that give you 5x minus 5. Pull out the 5 as a factor, so that give you 5 times x minus 1. You have to find the connection with the x minus 1. So this is what we did so far. The difference 5x plus 1 minus 6 is equal to the 5 times absolute value of x minus 1. That's a key example, key part of this problem of the limits. See, that's the L and that's the x0. You connect them together. Now the tolerance. This is the tolerance. They give you that this is less than 100, so substitute. So we say that, oh, bad. I wanted with this condition, 5x minus 1 minus 6 to be less than 1 over 100. So this means if you substitute here, so this means 5 times absolute value of x minus 1 is going to be less than 1 over 100. So this means absolute value of x minus 1 divided by 5, that give 1 over 500. Okay. Any question? So what is going to be 1 over 500? 1 over 500, if you multiply by the top and the bottom by 2, that give it 2 over 1,000. 2,000.002. So this means if you round the value of the x, okay, with this percentage of error, to get, let me just go to the next page to explain it. Remember, you are looking for the x. So we continue. So we have the absolute value of x minus 1 less than 0.002. Open up the absolute value, x minus 1 less than 0.002, greater than negative 0.002. Add 1 to both sides, 1 plus 0.002, and this would be 1 minus 0.002. Okay, if you subtract this, this would be what? It's going to be 0.998 less than x less than 0.1002. You see? This means if you pick your values of the x, you see, this means if you pick the x to be any number, okay, between 0.998 and 1.002, then it's guaranteed. It's guaranteed that the difference of the 5x plus 1 minus 6 is going to be less than 1/100. Nice proof of the limits. 1/100 is not important. You can pick any number you like. So this means, you know, if you arrange a table, in your table, you start from 0.998. You see, if you pick any number, you see this is it. This is 0.998. Okay, and this is 1.002. So if you pick any x here, if you pick any x here, then that x would satisfy 5x plus 1 minus 6 to be less than 1/100. Since you can do this one all the time, that's why the limit of the function 5x plus 1 would be equal to the 6, and then you're done. Okay, so it doesn't matter. This is 1/100. If somebody give you 1/1000, you just go back and check it again. You are going to be around the 1. You see, 1 is somewhere here. Okay, 1 is going to be somewhere here. So this is left limit or right limits, if you like. But if you pick any number in that interval, that would be the same thing. Any question? So this must be the description of the limits that you have to know, and we are going to extend that in a minute. You know, there is like this procedure is like rounding the numbers. You say rounding to the 10th place, rounding to the 100th place. This is going to be the same thing to get this true. Okay, any question? So when I teach Calculus 1, and I teach, you know, there is a course for the future teachers that I teach at the university. I ask them this question. Let me just write it down for you. You see, when I teach, this is going to be the case. If you like, we ask you to round this number, 1 point, okay, 1 point, let's say 1.43 and 1.46 to the 10th place, to the 10th. Okay, to the 10th place, or to the, yeah, to the 10th place. It's good to know, give you better understanding here. Okay, who wants to try? 1.3, 1.43. If you round it to the 10th place, what's going to be the answer? Round it to the penalty. Yes, 1.4, 1.4. Yes, you are right. So you know that the way you do it, they usually say that this is going to be the rounding place. So the next number is 3, so we drop it. So that gives you 1.4. Okay, very good. How about the second one? 1.46. This is going to be the rounding 10th place. So this is the 6, you know that since it's 6, it's going to be 1.5. So this is the way we do the rounding that we know, we just do it. Okay, so what does it mean, this one? Any suggestion? Because that's very much connected to the, the one that I did for you. And we are going to do in future. Can you describe the method? Okay, just what does it mean, this rounding that you did? Any comment on this one? You see, the comment is going to be rounding is an estimation. That's it. When you run the numbers, you do the estimations. When you do your estimation, you may lose something or you may gain something. So you have to give us okay, your tolerance, if you like. So when they say the rounded to the 10th place, means your tolerance is going to be at most, okay, at most 110. So you see the 1.4 that you find over here, look at this number. This is exactly what we did for the limits. This is 1.4. So when we say to the 10th place, you see that's a 110. If you divide the 110, you see that's a 110. If you divide it by 2, which is going to be equal to the point, okay, it's going to 0.1. If you divide it by 2, so that gives you 0.05. So your tolerance is, okay, if you go to the right and the left, you see your tolerance is you go 0.05 to the right and the 0.05 to the left. So if you add it to the 1.4, that gives you 1.45. If you subtract it, that gives you 1.35. So you see you get an interval here. You get an interval between, you see that's going to be your interval. This is going to be 135. And this is going to be, okay, 145. Just like the one that we did for the limits. You see, if you pick any number, this is 1.4. If you pick any number in this area and you round it to the 10th place, you arrive at the 1.4. You see, in limits, this x getting to the 1.4, but there is a restriction. Your restriction is that 0.05 that you did over there. Okay, and so there you have an interval. You see, you have this interval of 1.35, comma 1.45, and this must be open. So if you pick any number, you see if x is going to be, if your x is inside, then your x is going to be closer and closer to the 1.4. So your tolerance is going to be 1/10 that you do it. So that's the meaning of rounding to the 10th place means, really. Okay, that's the kind of calculus that you're going to have. For the function, you see, if you can do it all the time, then the limit of the function, limit of f of x would be, you see, that's what we did over here. Look at this one. So the way we did it, we create this interval. We create this interval for the x. If you pick any x in this interval, you guarantee that the f of x is going to be there. So since we can do it all the time, so in that case, we can say that the limit of the function when x goes to x0 is equal to the L. Okay, so I just want to give you this better understanding, because there are a couple of cases in this section and that you have to know this type of ideas to be able, to be able to get through it, and that give you a better sense of the limit of the function. Okay, any question? Let's go back to our question. So what is the function that we have? Okay, look at this once more to get to the definition of a limit of function two variables. Look at this one. So we want to just extend this definition that we have over here. You see, your function is going to be a function of two variables, f of x and the y. So it makes sense. F of x and the y would be a number, L would be a number. The difference is a number, we can use the absolute value. You have to change this part. The domain of the function of one variable, numbers, x minus x0. But when we function of two variables, we have points. So we change this one to the x comma y. Then we change this one to the x0, y0. We cannot use the absolute value for the points, but we can use the norm for the points. So we copy this formula, and that give us the limit of the function of two variables, and in future, three variables. Change this one into the norm, stay this one with the absolute value. The rest are all the same, and quickly you can bring everything in calculus one up here to be able to do the job. Okay, so but my suggestion is, if you haven't seen this type of problems before in calculus one, just read the other pages that I talk about it. If you want to take more advanced courses in mathematics. So that's a definition of a limit of a function of two variables. Very similar to what we did. There you are. Get a function now. If you are a math major, this is going to be your job from now on. You just work with this epsilon delta notation. And suppose a function the function of two variables, z equal to the f of x comma y. You want to consider the limit at a point is defined. Let's say near, like we do it in calculus one. Near a point, again, not number. A point. The point this time is going to be x0, comma y0. We have the L, as we talk about, an L is a number, a given number. Given number. Okay, then limit. We write. We talk about everything there, so we can extend it quickly. We write what? We write the limit of f of x comma y when x comma y, okay, get closer and closer to the x0, y0 is equal to the L, exactly as we did it, because f of x and the y are numbers. So again, the same thing, I can estimate f of x and the y by L. So if and only if, copy that formula that we did. If and only if, okay, if and only if the absolute value of f of x minus L, these are numbers, we can use the absolute value, goes to 0 whenever. Now the difference of the points, you cannot use the absolute value, you have to use the norm. Think about them as a vector, as a point in R2. If the norm of the x comma y minus x0, y0, okay, goes to 0. So exactly as we did it for the function of one variable. Okay, so when x and the y getting closer to the x0, y0, then f of x getting closer and closer to the L. Now the epsilon delta form equivalently. Equivalently, this is going to be the case. Again, now more precise. F of, limit of f of x comma y, the point x, y getting closer and closer to the x0, y0 is equal to the L, again, if and only if those estimate. I can make f of x and y as close as I wish to the L by forcing x and the y to be as close as x0 and y0, sufficiently close as I need. So it's the same thing. So if and only if for those percentage of error for a given positive number epsilon or epsilon, that's the estimation that you do. Yes, there exists, there is, okay, a positive number delta such that for all points x comma y in the domain of the D, whenever or if the norm of x comma y minus x0 comma y0 is going to be less than delta, then the difference f of x minus L to be less than epsilon. So that's the extension of the definition that I did for you in two-dimensional. This is a two-dimensional. So it's very much similar, but we have to change this one. You cannot use the absolute there, you have to use the norm. And that would be fine, but in your book, they changed this norm into the formula. I just recall that. I'm not going to do it, but sometimes we need it. Recall that the norm of the x comma y is it's a distance between these 2 points, really. Remember, is the square root of distance formula. X minus x0 all squared plus y minus y0 all squared. It's the way you know it's used in your book, but we don't need it. We just keep it as is. Especially if it is going to be 0, 0, you need this one only. In particular, if you have the norm at 0, the limit at 0, because we use the 0 only. So in that case, this x0 and y0 would be 0, so simply we get x squared plus y squared. Okay, that's it. Nice extension, and we have some nice problems. So far so good. You see, you haven't had any difficulty to extend whatever you have before. So we have various formulas. Remember, the limit of a sum of two functions or sum of the limits, the product, the quotient, everything would satisfy because you already got the other side. So just give you some preliminary examples to see how we're going to operate. Everything you learned before, it can be used. So far, you have no difficulty to applying this type of definition. Any question? So since we extended the definition, so we have calculus 1, bring it up. Okay, remember you have a theorem, we call it computing theorem. How we're going to compute the limit of a function. So you know that the limit of a sum of the limits, the product, the quotient, the square root, cube root. And basically, if you want to find the limit of the polynomial, remember, direct substitution give you the result. Use all of them to get these numbers. So I give you a couple of examples. You get quite a lot in your book. And one question would be given to you. There is nothing difficult about these ideas so far. Okay, so this is it. This is your job. Nicely can be done. Find each limit. Use any theorem that you know from calculus 1. Find each limit. First one, limit of 5x cubed y squared minus 9. Okay, when x comma y goes to 1, 4. That's the first one. Just want to show that how we're going to do it, and you're not going to make it complicated for us. You see, you know that this is a polynomial function. It's a polynomial in two variables. And as we did in calculus 1, if you want to find the limit of a polynomial, direct substitution. You replace x by 1, y by 4. Simplify it, you're done. That's it. Solution. So I rewrite it. So 5x cubed y squared minus 9 x comma y goes to 1 and 4. Substitute. 5 times 1 cubed times 4 squared minus 9. Simplify. It's going to be 5 times 16 minus 9. 80 minus 9. 71, and you're done. That's it. Because it's a polynomial function. Question? Because you extend everything, so there is no need for anything complicated. It for second one. How about quotient function? The limit of 5x squared y, x squared plus y squared. You want to find the limit, x comma y goes to 1 and 2. That's it. Rational function. The top is a polynomial, the bottom is a polynomial. So you want to find the limit, you just direct substitute again. Okay, directly substitute to get the result. Solution. Okay, this is it. The limit of 5x squared is y. I just repeated, you don't have to. So it's going to be x comma y goes to, you can do it right away, just substitute. So the top is going to be 5 times x squared, x is 1, times 2. The bottom one was going to be 1 squared, and that would be 2 squared. So the top would be 5 times 2, which is 10. The bottom one squared is 1 plus 4. Okay, 1 plus 4, so that gives you 10 over 5, which is equal to 2. The limit is 2, and you're done. Any question? So don't be surprised. These are going to be the case that we have. And for the next one, you can have all sorts of function. So don't be surprised if you get the limit of the sine of x over y. And this is when x comma y goes to 2 pi and 4. Okay, you know that the sine function, it doesn't matter, just substitute. So directly substitute solution. Again, you can substitute right away, but I explain it. Limit of the sine of the x over y. Okay, x over y, again, when x comma y goes to 2 pi 4, substitute, x is 2 pi. So it's going to be sine of the 2 pi. Y is 4. So that gives you sine of the pi half, which is equal to 1. Okay, so don't be surprised. You can use, because that's a real valued function in all of them. Again, you can have an exponential function like the limit of x e to the y z Is it 3 variables, X, Y, Z? Just want to remind you. So is the limit when X, Y, Z, X, comma, Y, comma, Z goes to -2, 1, 0. It doesn't matter, exponential function, you know, that's kind of a continuous function. So you just get the direct substitution to get the result. Okay, so you have the limit of X, e to the Y, Z. Again, you just do it. Goes to -2, 1, and 0. So X is a -2, Y is 1, Z is 0. So it's going to be equal to the -2 e to the, okay, Y is 1, Z is 0. So that you -2 e to the 0. E to the 0 is 1. -2 times 1 equal to the -2. And then you're done. Okay, so far so good. Any question? Now, you have a couple of, at least 3 problems in your book, like the next one. Let's say we're going to handle the next one. Okay, are you done? You see this one? You did have a similar one of this on your, okay, before. Let's see, so number, it's number 4. So we go with 5. We go with the 5. What is this one? Limit of x squared minus y squared. And this is going to be x minus y. X comma y goes to 1, 1. Okay, any suggestion for this one? If you direct substitute, what are you going to get? Directly substitute, we get the, yeah, we get 0, 0. Okay, we get the 0, 0. Okay, 0, 0. What does it mean? Or what are we going to do? Okay, 0, 0 means, I know if you're going to be in calculus 1, we can use the L'Hopital rule to do it, but there is no L'Hopital rule for the function of 2 variables or 3 variables. But there is something else that you can do. No, you can't use the L'Hopital rule. L'Hopital rule cannot be used. Remember, another meaning of the 0, 0 means the top and the bottom would have a common factor. So you have to factor it. The common factor would be, in this case, x goes to 1, that gives kind of x minus 1. So what you have to do, you have to factor the top and the bottom, eliminate that common factor, and just do it. It's the only way that you can do it, okay? No L'Hopital rule for the function of 2 variables, okay? So be careful. So the solution is going to be, yes, if we substitute, I just remind you that we do the substitution as usual. Okay, this is x and the y goes to 1, 1. We arrive at the fact that the 1 minus 1 on the top, 1 minus 1, so that gives you 0, 0. So you have to factor it to find those common factors, and then you'll be able to do it. So we rewrite it, you see, limit of x comma y goes to 1, 1. So the top would be x minus y times x plus y. And the bottom one would be x minus y, you see. Now we eliminate the common factor. So the leftover is going to be the limit of x plus y. And it's going to be the case when xy goes to, okay, xy goes to 1, 1. Any question? Now we substitute. It's 1 plus 1. which is equal to 2. So the limit would be equal to 2. Okay, so be careful. 0, 0. This is the way you do it. You need one more example. You have a couple of them in your book. Let me just check. I don't have it here. I know that it's like what is going to be the case. Let me just tell you the number that you have. Just give me a couple of seconds. So you have a group of them. You better check it. And you see it in your next practice quiz that you have. So it's in that is 12. This is where we are. Must be 12.1. Oh, I'm sorry, 13. Chapter 13. Just want to show you where is this app of the limits. I think we are in fact in 12.2 now. 13.2. And where is those limits? Yeah, they are here. You see, it's a 13.2, these examples that I'm going to do for you. And you have a collection of limits. You better go through these. Just pick a couple of them. But there are a couple of interesting ones are here. You see, look at this one. You have two here. It's number 29. It's not from number 27 is the one that I did. Okay, 27, like the one that I did. 27, 28, 29, and 30. The best one is this one. Is 30. I'm going to explain this one. Okay, this is a little bit different from all the other one, but the other groups are easy. So we are in 13.2, the first part, of course, because there is a continuity. We're not going to finish it. So let me just give you an as a next example to make sure everybody know this method. Okay, so in my edition, this example is going to be, I have it in 13.2 or the similar one. And this is problem 30. So look at around this problem. Just make sure you know it. So don't be surprised if you get it on the test. Okay. So that was the limit of. So this is it. You want to find the limit of. I just closed the book. It's x minus 1 minus 1, I think. That was the one. I did have it in somewhere. Let's check it again. Okay, there you are. It's the x minus y minus 1 on the top. X minus y minus 1 on the top. And then the bottom, we have the square root of x minus y, then minus 1. And you want to find this limit when x, if you take any calculus book, in calculus 3, you will see this example. It doesn't matter which book it's going to be. Okay, so this is it. Okay, you want to find this limit. See what is going to be special about this one. Okay. Yeah, that's one. That's correct version. So, as usual, we try, we substitute to see if we can get it, but this is not going to be the case probably. So the solution is going to be if we substitute directly. So x is 2 minus 1 minus 1. Okay. And this is 2 minus 1. And we get the negative 1 here. So the top, we get the 0. Okay, the bottom one is the same because this is a radical 1 minus 1. which is going to be 0, 0 again. Okay, so the 0, 0, but I told you, you don't have the L'Hopital rule in function of two variables. So we go back to see so we should get that common factor again over here. Okay, any suggestion? Do you remember how you do these type of problems when there is a radical here? In calculus 1, you have to do algebraic operation called, that's it, yes. Yes, you are right, Donatas. You have to rationalize it, remember? You have to rationalize the bottom one, you multiply the top and the bottom by the conjugate of the radical expressions. Conjugate of the radical expression would be radical x minus 1 plus 1. If you multiply, that radical would disappear and that factor, common factor would disappear, and then you'll be done, okay? So you may, you see, you may factor it right away as a polynomial type, as we do in calculus, function of one variable. Over here, multiply the top and the bottom by the conjugate, okay? So there you are. You have the limit of x comma y goes to 1. Okay, so you already got the x minus y minus 1 multiplied by the conjugate of the denominator. That's a conjugate. The x minus y plus 1. Okay, you do the same thing to the bottom. So the bottom, you have the x minus y already. Now multiply by the conjugate, which is a radical x minus y plus 1. So you should arrive at the common factor. Okay, so we focus on the bottom one because we want to get the common factor. So it's going to be equal to the limit of, okay, that's x, y goes to 1. Okay, denominator, you know, there's going to be a square of the first minus the square of the second. I write down, but you can do it right away. Square of the first minus the square of a second. The top is going to be unchanged. Okay, radical x minus y plus 1. Now, the bottom one would be that common factor that you are interested in. That gives x minus y minus 1. And on the top, you already got the x minus y minus 1. So we can cancel it out. So that gives us x minus y plus 1 outside. And that's the x, y goes to 2 and 1. Now we got the time that we can cancel out these two. So that was the plan. Any question? So you get the leftover and substitute. So it's going to be limit of the leftover is a radical x minus y outside plus 1. Okay, when x comma y goes to 2 and 1. Now substitute x equal to 2, y equal to 1. 2 minus 1 plus 1. So that give a radical 1 plus 1 is going to be 1 plus 1 equal to 2. The best case of this type of problems. Okay, so be careful getting this, this type. Any question? There is one more type. I'm not going to give you anything else today, okay, in case you want to take your test. And that next example is going to be quite different. We have to do it directly by definition, and that will open up another argument that we are going to look at the limit. You see, the difficulty with this type of problems are going to be the one that sometimes you want to find the limit and you want to show that the limit does not exist. In calculus 1, you go with the right and the left limits, but it doesn't make sense here. So we have to do something else to be able to take, the next group of examples. So that would be the first part. Okay, so I'll let you go today. I'll give you early, just if you want to take the test, and we already got enough for today. So just have a look. We get time, the type of function, get to know this function, okay? And so far, everything is going to be the same, but as soon as we get to the next theorem, the difference is going to be when you want to